Welcome back to The Explainer. Today we're diving into a massive, honestly mind-blowing topic. We're looking at one of the ultimate man versus nature challenges out there, engineering and building a highly precise maritime facility on a harsh, incredibly remote coastline. Just imagine looking at an empty, windswept desert beach and deciding, you know what? I'm going to carve out a fully functional 100-meter class harbor right here. It sounds impossible, right? But through this incredible blend of geology, physics, and sheer human ingenuity, it actually happens. So let's jump right in and see exactly how engineers pull off this monumental feat.
Here's our game plan for today. We'll start by surveying the hostile coast, then carve out the harbor basin, build up the breakwater shield, engineer the quay walls, and finally, defend the whole thing against the elements. Let's get to work.
Starting off with Phase 1, surveying the hostile coast, the pre-construction phase.
Now, long before a single rock is even dropped into the water, engineers have to map out some invisible threats. You might think building a harbor is just about pushing dirt around, but first, they have to run extensive hydrographic and geotechnical surveys. They're using sonar and boreholes to really understand the seabed. Why? Because in these desert environments, you're usually dealing with loose sand sitting right on top of much denser rock layers. If you don't know exactly what's underneath you, your entire harbor could literally just wash away. But they also have to map the ocean's behavior itself. Think about this baseline metric for a second, 1 to 3 meters. That's the typical offshore wave height during a storm in a moderate wave climate. That is literally a wall of water up to 10 feet tall, constantly slamming into the coast with immense kinetic energy. That is the terrifying baseline of the wild ocean that our engineers are up against.
Okay, now contrast that massive, violent wall of water with our ultimate target, less than 0.3 meters. For a small vessel to safely dock, load, and unload, the wave heights inside the harbor basin cannot exceed that mark. So the absolute crux of this whole project is that engineers have to design a structure that forces a chaotic 3-meter ocean storm to chill out into a gentle 1-foot ripple by the time it reaches the boats. How in the world do they do it?
Well, that brings us to Phase 2, carving the harbor basin with earthworks and excavation.
To carve out our design depth of 3 to 6 meters, they rely on some seriously heavy excavation. We're talking a two-pronged approach here, dry land excavation from the shore combined with nearshore dredging out in the water. But here's the catch. You can't just dig a massive square hole in the sand and expect it to stay put. The secret is all in the math behind the dirt. The basin slopes have to be cut at highly controlled 1 to 2 to 1 to 3 gradients. These specific angles aren't just for looks, they are mathematically absolutely crucial. If you dig straight down, the sandy subsoil will just collapse in on itself under the weight of the water and gravity. By grading it precisely to those angles, the soil actually remains stable. And as a cool bonus, all that excavated material is incredibly valuable, so it gets completely reused as structural fill later on in the project.
Next up is Phase 3, building the breakwater shield, specifically the rubble mound defenses. This breakwater is our primary defense against the ocean. It's what takes the hit from those 3-meter waves we talked about. It's essentially a giant engineered mountain of rock extending out into the ocean to act as a permanent shield. But it's definitely not just a random pile of rocks. It's a precisely layered system built from the inside out. Step 1 is the core layer. This is the bulk of the structure, made of smaller rock fill, often using the exact material we just excavated. But if you stop there, the waves will just suck those small rocks right back out to sea. So Step 2 is the filter layer. These are medium, really carefully graded stones that trap the core inside and prevent washout. And finally, Step 3 is the armor layer. These are the massive, heavy quarry stones or precast concrete units on the outside that take the direct punch from the ocean.
But how do you know exactly how big those outside armor stones need to be? You can't just guess, you use physics. Engineers rely on wave stability formulas, and the most famous one here is the Hudson equation. This formula calculates the exact size and weight of the armor stones required to ensure that when a massive wave hits, the individual blocks don't just get picked up and tossed around like pebbles. Every single stone is mathematically guaranteed to resist those incoming wave forces.
To give that math some real-world physical perspective, check out this number. For moderate wave climates, the individual armor units on the outside of the breakwater have to weigh anywhere between 1 to 5 tons. Now, a typical car weighs about 1.5 tons. So you're basically looking at carefully placing rocks the size and weight of an SUV or even an elephant, one by one, to build a wall against the ocean. It's just staggering when you really think about it.
Moving inward, we hit Phase 4, engineering the quay walls, the 100-meter hearts of the harbor.
This is the true heart of the whole operation. The dual 100-meter quays, where vessels actually tie up, berth, and unload. These walls sit right at the boundary of land and water, so they have to be incredibly strong. Engineers typically choose between two brilliant structural solutions here. The first option is the gravity quay wall. This is pretty much exactly what it sounds like. Massive concrete blocks or caissons stacked on top of each other. It relies completely on its own massive self-weight to sit firmly on the seabed and hold back the earth. The alternative is the sheet pile quay wall. For this one, heavy steel sheets are driven deep down into the seabed. But because steel bends, engineers have to anchor the top of the steel wall deep inland using heavy tie rods and then backfill it with compacted earth to hold it tight. Honestly, both are total engineering marvels.
And they have to be marvels because they're constantly under attack from four distinct, immense forces. First, mooring loads. When a ship ties up, the wind pulls the ship, which pulls the ropes, putting up to 150 kilonewtons of tension on the bollards, literally trying to rip them right out of the concrete. Second is berthing energy. A heavy ship slamming into the wall generates huge force, which has to be absorbed by thick rubber fenders. Third, live loads. You've got heavy trucks and cranes driving constantly right on top of the wall. And finally, scour effects. Every time a ship turns its propellers, it creates a powerful jet of water that tries to erode the sand right out from under the wall's foundation. So yeah, it is a relentless battle.
Which leads us perfectly into our final section, Phase 5, defending against the elements with logistics, hydrodynamics, and durability. Executing a design like this in a remote desert location means it's definitely not an overnight job. It's a massive, multi-step logistical journey. Phase 1 is just building temporary access roads so you can even get your cranes and concrete trucks down to the beach. Phase 2 is dropping the breakwater core. Phase 3 involves the meticulous installation of those 5-ton armor rocks using massive cranes. Phase 4 is constructing the quay walls and backfilling the earth behind them. And finally, Phase 5 is the last round of dredging and finishing out the basin to get it to that perfect 3 to 6 meter depth.
Now, remember our main goal of reducing those huge ocean waves down to a tiny ripple? A critical piece of that hydrodynamics puzzle is the harbor entrance. Engineers run complex, numerical computer models to dictate that the entrance must be strictly between 20 and 40 meters wide. Why so specific? It's a delicate balancing act. It has to be just wide enough for ships to navigate through safely, but narrow and angled enough to minimize the wave energy coming in. If it's even a little too wide, the storm gets inside.
And to survive decades in this incredibly hostile environment, standard materials just won't cut it. Engineers have to heavily upgrade their materials to fight back. They use sulfate-resistant concrete because normal concrete will just get eaten alive by the chemicals in the salt water. They use coated or galvanized steel to stop relentless rust. They have to source specifically high-density armor rock so it doesn't shatter upon impact. And they lay down heavy concrete mattresses on the seabed directly in front of the quays to fight off that propeller scour we mentioned earlier. Every single detail is hardened for long-term survival.
So after breaking down all the sonar maps, the Hudson equation, those SUV-sized rocks, and the anchored steel walls, we really have to ask ourselves, how does this precise balance of geology and physics transform an exposed, completely hostile shoreline into a permanent sanctuary? The answer is that absolutely nothing here is left to chance. Every single slope, every rock dropped, and every poured concrete edge is a highly calculated interface between the land and the sea.
I want to end today's explainer on an incredible quote from our source material because it just hits the nail on the head. In places where nature offers no shelter, engineers build one, stone by stone, meter by meter, transforming an exposed shoreline into a safe harbor. It truly gives you a profound appreciation for the unseen math, the sweat and the steel beneath every single port. So the next time you stand safely on a quiet concrete pier, looking out at the water, ask yourself, what invisible, violent battles are being fought beneath your feet right now just to keep you safe?